Swayam Prabha. Digital India. Educated India.
Okay, good evening. So, we were looking at a continuous Markov process. One such example was the Wiener process, right? So, the Wiener process is characterized by the characteristic functions A0 and B is taken as 1, right? So, then this yielded the distribution function like this, right? Now, so this is basically a Gaussian random variable, right, with the mean of x is 0 and the variance is equal to time t. Okay, so variance actually grows linearly in time t. Now, even though we were looking at this more from a mathematical point of view, this process, Wiener process, explains the dynamics of free Brownian particles position. Okay, so Wiener process for the position of free Brownian particle. Where x of t is given by square root of 2d wt. Okay, this should be, yeah. So, you can generate random variable w of t from this distribution, okay, and then when you multiply by the square root of 2d, this will take care of the Brownian particles diffusion. Okay, or if you go back to this problem and then instead of 1, if you take 2d, you will get the expression for Brownian motion. Okay, so this is actually not p of x, it should be p of w, and so this also is mean w, like this. If you were to choose a as 0 and b as 2d, you will get p of x comma t or basically 4 pi dt. Okay, so this is for function b1, this is for b equal to 2d. So this kind of gives you directly the Brownian particles, free Brownian particles position. And if you want to use this Wiener process can also be used by properly scaling the variance. Okay, so we have seen these things in the last class. So now I want to look at another class of problems. These are called Ornstein-Uhlenbeck processes. Ornstein and Uhlenbeck, these are the scientists' name, okay, who developed this theory. So here, before we look at what that is, we will consider two cases. One is Brownian particle bound to a harmonic spring. This is for a Brownian, this for a free Brownian particle position. Okay, so now you may have another system where you are thinking about a Brownian particle which is bound to a harmonic spring, and you are interested in the position of the Brownian particle. We looked at this problem in the context of Langevin equation before. Now we are actually looking at the same problem from the Fokker-Planck or the continuous Markov process standpoint. The second case is a free Brownian particle whose velocity is of interest to us, right? So these are two different problems. So here we are talking about free Brownian particles position. So here I am talking about free Brownian particles velocity. I wanted to describe the velocity of a Brownian particle, free Brownian particle, as a random or stochastic process. Here I have a Brownian particle bound to a harmonic potential, and I am interested in the position. Okay, so now we look at the physics of this problem, and then we will show that both of this problem actually has the same kind of characteristics in terms of how we define functions a and b, so that these can be grouped together as one class of problems, which is what we are going to call as Ornstein-Uhlenbeck problem. Okay, so let's look at from the what we know about these process from the Langevin point of view, and then we'll come to the Fokker-Planck formulations. So in the Langevin approach for problem 1, you would write m d square x by dt square, okay, m times the acceleration is equal to minus friction coefficient times dx by dt minus kx plus 2 gamma k bt eta t. So if you want to model a Brownian particle's position when it is bound to a harmonic spring, you write that mass times acceleration is equal to the drag force, which is minus friction coefficient times the velocity minus kx. This is the spring force opposing the particle's motion, and this is the random thermal noise. Okay, this is how you would model the position. So now if you consider the overdamped limit, so overdamped limit basically means looking at time scale t much greater than the initial time, in which case this initial term drops to 0. Okay, so you equate these things to 0, so you will get dx by dt minus k by gamma x plus so the Langevin equation, when you write for overdamped limit, this term is 0, you take this term to the left and divide the expression by gamma. So you will get dx by dt on the left hand side is equal to minus kappa by gamma x plus this entire term divided by gamma. So you get 2 kt by gamma. Okay, and this 2k, the kbt by gamma is nothing but diffusion coefficient. So you can simply write 2d. Okay, so this expression basically tells you if you solve this, you can find how the position of a harmonically bound Brownian particle will evolve in time. Yeah. So now if you want to cast this problem in terms of a Fokker-Plunk equation, this function a of x comma t, this is given by this term. So this function a is proportional to x with some proportionality constant. Function b is basically whatever is there inside the square root. So that is actually 2d. So the problem that we have set up in terms of Langevin equation, if you want to write this in terms of Fokker-Plunk equation, the function a, which kind of tells you about drift, is nothing but the term that is the first term, and the b is going to be the term that is within the square bracket. So this is an important result to model a Brownian particle confined to a harmonic spring by choosing these are a and b. Now similarly, let us look at this particle, a free Brownian particle, and you are interested in the velocity, right. So again we go with the same equation like here, m you have this term, this is a free Brownian particle, so there is no spring force here. Now here it is written as a second order ODE in terms of position, but we are actually interested in the velocity. So we will write dx by dt as velocity. So you would write m dv by dt is equal to minus gamma v plus square root of 2 gamma kbt by m square. So now this is going to be the governing equation, the Langevin governing equation to describe the velocity of a free Brownian particle. Okay, and this is something called the underdamped. We say this is an underdamped Brownian dynamics, meaning that this equation is actually applicable for all times. Okay, whereas here we said it is overdamped, it is only applicable for time larger than the initial time. Here this equation is applicable for all times, for t even less than equal to t inertia. So now if you think about v here as a random variable, so here we had x as a random variable, the position as a random variable, position as a stochastic variable. So here we have velocity as a stochastic variable. If you look at the functional form of these two, they are very similar. Okay, so here also we can set up a Fokker-Plunk equation with a characteristic function a of v comma t is equal to minus gamma by m v and b of v comma t as the term that is inside this bracket, which is 2 gamma kt by m square. So what we are seeing is that we have two problems, and then when you look at both problems from the Langevin equations, and then when you look at from the point of this characteristic equation for Fokker-Plunk, you see this a is proportional to or linearly dependent on the random variable x here with some constant k eta. Remember, k is positive, spring constant is positive, friction coefficient is also positive. Okay, so this minus sign is there, and this b function b here, which kind of characterizes the mean square rate of change of mean square values, that is constant. Okay, similarly here if you take the characteristic function a for describing the velocity of a free Brownian particle, also has a linear dependence on v itself, and the b function is constant. This is a constant. So therefore it seems that there is a set of problems for which a is proportional to the random variable itself, in this case proportional to x, here this is proportional to v. So a is a function that can be written as minus, let us write like this, a of okay. By looking at these two problems, we can define a class of stochastic process such a way that the characteristic function a is equal to negative minus some constant a, positive constant a times the random variable u. Okay. So here u means x, there u means v. Okay. So here I am saying u as a some general stochastic process. Okay. And then b, the characteristic function b is given by some constant. This value of b for this problem is equal to 2d, whereas for this problem b is this. Okay. So therefore we can solve a Fokker-Planck equation for a set of a and b values based on this rule. Okay. I already remarked that in the case of Wiener process, a of u comma t was 0 and b of u comma t was 1. This is one class of problem which we call as a Wiener process. Now we have another situation where a is not 0 anymore, a is minus some constant times the random variable itself. Okay, it changes linearly, and then this function b is a constant, some arbitrary constant. Any stochastic process that has this functional form is called Ornstein-Uhlenbeck process, and this process on its original form was used to characterize Brownian particles bound to a harmonic potential, also free Brownian particles velocity. Okay. So now we will take this as the characteristic functions, go to the Fokker-Planck equation, solve and see the characteristic of the solution. What is that we get from this, right? You are with me? 5 o'clock on a Friday, not a good time to study stochastic process, right? It's like probably the most less likely just think about it, take a couple of moments, just see what we just discussed, and then ask me if you have any questions before we go further. Yes. V is the velocity of a Brownian particles, which is a stochastic process. Okay, it has an underlying distribution. That's what we want to find out by solving the Fokker-Planck equation. Only why this part is the, yeah, so that's what I'm saying, that if you write these the problem in a Langevin formulations, right, the rate of change of this, okay, when you have some sort of a non-zero value, the first term that is related to the drift, this which is a random the diffusion part. Okay, so remember that this is a normal random wise, this is basically multiplied by the sigma. So this is sigma, b is nothing but sigma squared, so that's why I'm taking 2d. So generally when people actually think about this kind of process, they argue and discuss how to define a and b. What I'm trying to show here is you can start with the Langevin framework because that's more intuitive, because we know the physics of the problem, we know what terms to add, and then when you write the rate of change of the differential, the rate of change of the variable, in this case dx by dt, here dv by dt, and then you can put all the terms to the right. The first term tells you the drift, rate of change of x, this part is a, and this part is the diffusion part, which is 2d. Suppose if I had a free Brownian particle, if I write this equation, this term would have been 0, right? So actually my a is 0, and I have only this term, which is the diffusion term. So therefore, for any given problem, you first start from the Langevin point of view, because that's more intuitive to write, and then you cast the equation in terms of dx by dt or dv by dt or du by dt, and then you look at the terms, okay, and and then match these coefficients. Yes. Yes. Generally, these are treated separately. You look at either the Fokker-Plunk formulations or Langevin formulations. But in this course, as I said in the beginning, that we are trying to put all of them in the same context and try to see the interrelationship between different framework, so that we can adapt the framework that is more easy to handle. If you recollect, Brownian particle confined to a potential, we solve that equation from the power spectral density point of view in the Fourier space. Why? Because there is a measurement that is made in the Fourier space using optical tweezer, so we can directly connect the power spectral density of the measurements. Okay, so depending upon how you want to use this dynamics, so you have to use either Langevin approach or Fokker-Plunk approach or chemical master equation approach. So those are the three different classes by which you can handle pretty much every stochastic process out there. All right, okay, so let's go to the Fokker-Plunk equation. Here, maybe yes, yeah, there is a negative sign there, yes. So this becomes plus now. So we start with the Fokker-Plunk equation and substitute for A and B. Okay, A is substituted as this constant A times U minus, and then this B is constant taken out. So you have to solve this equation now. Okay, so I will not discuss the entire solution, but I will probably just give the intermediate steps. What we would like to do is define a function. This process is same as how we did the Wiener process. du e power I s u. Okay, so we transform the variable from u to s based on this Fourier transform, and then this partial differential equation will become a this becomes dou phi by dou t plus as dou phi by dou s is equal to minus b by 2 square phi. So using that transformation, when you apply to this Fokker-Planck equation, you get this equation, and this can be solved. So we do the inverse Fourier transform to calculate to get p of u comma t with the initial condition of u naught t naught. This will become so this kind of gives you the full distribution that how u will change with respect to time t. Such a messy expression that that you will get. But what happens is that if you look at this solution at a long time t tending to infinity, this becomes a stationary distribution. Okay, and that is what more interesting to us. And so we look at the solution at the time limit t tending to infinity, so that we can look at steady state distribution. Yes, I think so. Yes, it is actually in the exponential of entire thing. Yeah. Yes. But you can clearly see what is the functional form. This is actually a Gaussian form. It's just that you have to find what is the mean and the standard deviation from this. Okay. So here you will see that the mean of u is nothing but x minus x naught square. So this entire thing is your mean value, u naught e power minus a t minus t naught. Okay, so that is your mean value, and then the variance is b by 2a into 1 minus e power minus 2a t minus t naught. So this basically is a Gaussian distribution with the mean of this expression and variance of this. Okay. So now if you set at the time t tending to infinity a long time limit, you will see that the mean value of u tends to 0, right, and then sigma square simply becomes b by 2a, right. So these are the steady state solution of the Ornstein-Uhlenbeck process. So now what we can do, now we can say what if u is the position of a Brownian particle bound harmonically. Then I know what is a and b, I can substitute and I can find whether this result conforms to the Langevin approach. Similarly, I can think of this u as the velocity of a free Brownian particle for which I know b and a, and I can check whether this is conforming to the solution or not. Okay. So let's do that. So we say that u here is actually x, the position of a Brownian particle confined by a harmonic potential. So in this case, our a E of x comma t was k by gamma x. Okay. In other words, in this equation, wherever we have a, we have to replace that with k by gamma, right, and then b was considered as 2d. So that means wherever we see b here, we should be replacing that with 2d. So what that means is, by this we would predict that the mean value of x is 0 and the mean square displacement is 2d over 2a this. So this is actually a mean square displacement of harmonically bound Brownian particle position. Okay, and this is a value we got from the Langevin approach as well. Yeah. Sorry. the Langevin equation with this particular functional form is analytically soluble, but if you have some other functional form, for example, you get dx by dt equal to sub minus kx squared, right? So then A will not have this kind of a form, but you have some kx square. Then you have to again redo all the Fokker-Planck equation for this functional form. So right now, this solution, steady state solution, is only valid whenever you have A and B defined in this way, any process. So here I am giving an example of two processes. One looking at position of a Brownian particle confined to a harmonic potential, that's one type. The other type is free Brownian particle. Here I am not interested in the position, but I am interested in the velocity. In each case, when you look at the functional form of A and B, they have the same class, that the function A is linear in the random variable and the B function is a constant, right? Yeah. Come again? Yes. So here I am all doing one dimensional random variable. Yeah. So now what we can do, we can go to the second process, that is free Brownian particle velocity. What is the value of A? This was minus gamma by m v, and B was 2 gamma kBt over m square. This was B. So in this case, we see that the average velocity will go to 0 as t goes to infinity, and then the variance of velocity v becomes b by 2a. B is this, and a is gamma by m. Gamma cancels, you get kt by m. And this is nothing but the mean square velocity, and we see that the kinetic energy of this basically comes as simply kBt. If you recollect, we use this kind of equipartition principle when we dealt with the Langevin equation for free Brownian particle, to write what the magnitude of the fluctuating force has to be. Okay, so that's what we kind of prove here also, so that they are all consistent. So what we are trying to say from all this thing is that the Wiener process and the Ornstein-Uhlenbeck process actually characterize a class of problems which all have the characteristic A and B functions. Okay, if A is 0, B is a constant, Wiener process. Okay, any stochastic process that satisfies those two conditions, you can readily apply Wiener process to describe. The next complication or the next sophistication is A is not 0 anymore, A has a linearly dependent functional form and B is still constant. Then we call that as a Ornstein-Uhlenbeck process, and you have a class of problem we can solve with that sort of things. Okay. Now, given a new situation, okay, let's say I give you a new problem. and then you have to look at, write the corresponding Langevin equation, and then see what the A and B values are going to be. If A and B values satisfy Wiener process or the Ornstein process, you don't have to really solve anymore. You know all the solutions, you have to just map the coefficients and you'll get the steady state solution directly without solving anything. On the other hand, if you are looking at a new situation where the A and B functions are not necessarily like this, then we have a different way of we have to solve them differently. Okay, so that's the important message I want to convey. Now I want to give you a small assignment in the class. 5 minutes, Google search, find the application of OU process. Okay, tell me at least couple of examples, applications, then you are free to go.